Let's post on the socials, I think. Twitch, am I live? I think so. Cool. Okay, let's go to Twitter. Oh. All right. For my YouTube viewers, because I get so many nice people watching these streams on YouTube. So today's stream is going to be writing a new memory allocator for the physical memory manager. And we're going to be doing the SLOB algorithm, which is probably one of the simplest things we can get away with for now. So it gives us a nice, easy, kind of like fragmentation free, well, not completely free, but it helps with a bit of fragmentation. It frees memory properly, not like the bump algorithm, which is a bit of a hello world thing. So this is a bit of a semi-serious algorithm for the kernel, and later on I'll build from this algorithm and upgrade it to a what's the next one, SLAB. But yeah, we're going to be starting with the SLOB, which is the simple list of objects. So this is going to take me a couple of hours, so this should be a fun stream, I think. Okay, so I've just fleshed out the header and the source file where this is all going to go. What I'm going to do is rely on the memory map that's been initialized in the memory manager. Should I say the PMM? There we go. Oh, where did my music go? So yeah, we're gonna we've already got part of the memory map defined for us from the bootloader. So our current physical memory manager manages individual pages from the memory map. So we're going to be reading the memory map again, but we're going to be setting up the SLOB structures instead of using a bitmap. So how the existing one works is if I could just get rid of this include folder, it's getting a bit noisy. So the existing physical memory manager at the moment is using a bitmap to identify pages of memory that are allocated or not allocated. So the SLOB allocation, I'm just going to draw it out for my mental picture right now. So we're going to have sections of memory on initialization. So these are like the buckets of memory. And this is going to be a free chunk. This is going to be a reserved chunk. This one will be free, and we'll just say for demonstration's sake this is reserved. So we're going to go through the memory map entries, and for every time we meet a free chunk, we're going to define this as a structure that is going to be set up as a linked list. So it's going to be kind of like SLOB entry, and we'll have a next entry pointing to the next SLOB. So this free block here will be a SLOB, and then this one will point to the one that's defined over here, and this will be our initial setup. Now I'm going to have size and what else do we need? Just size for now, so that when we're allocating memory, we're iterating through the SLOB entries. We're checking the length and we're going, has my SLOB entry got enough room for the memory allocation? And if it does, we're going to start splitting this guy up. I'm thinking though, shall I have a double linked list and have the neighbors or the previous node? I'll think about that when I'm in the implementation. So what we'll do at the beginning, so let's get this initialize function set up, and it's going to be starting its life by walking the memory map. So let me just grab these definitions, bring them up here. And SLOB 3. So we're going to need a SLOB init here. I'm so tired today, but we are soldiering on. Okay, so let's just set our tasks out in a few comments. So let's walk the memory map and create our SLOB entries. We're going to need a initial, well, we're going to first define the struct. Guess we'll just call it SLOB entry for now. and type def. And now we wanted the size, didn't we? Should we use size T? Unsigned long. Yeah, that's fine. I am going to put this attribute on. Oh, actually, no, I don't need to align that. I'm wondering, when I allocate a block of memory from the SLOB entry, it's going to split into a new SLOB entry, but it's going to be hidden away in memory. Okay, another thought for when we get there, actually. We can just take this one step at a time. So let's first walk the memory map. Now, we have got mem in here. We've got the mem map in here. So I'm just going to go pinch this here. And flip that to usable. So this is just walking that memory map from the bootloader, grabbing the struct for the entry, and then we're checking this type, which tells us if this block of memory in the list is usable. And if it is, we're going to go ahead and create a SLOB structure. So interestingly, where am I allocating my SLOB entries in memory? Shall I? I could dynamically allocate them at runtime. But I don't know how many I'm going to need. So we're going to have to do an initial path on the memory map. Okay, now that we know, shall I pick on the first thing? I think I do this in the physical memory currently when I define the bitmap. And then I adjust the page. Where are you? Print, get 3 pages, create the entry map, finds a memory, store the entry map, allocates it, stores a pointer. Change the values in the map. Yeah, we could do this. Hmm. I love this trance music. It's like, it's just a good enough rhythm. Oh, you won't be able to hear it on the YouTube video, but when I'm live streaming, I'm playing music and I can't record it into the VOD because copyright issues. But it's such a good piece of music to like just keep my head in a rhythm, keep the focus, you know? Da, da, da. I'm wondering to make this a generic function that passes in gosh, it's a bit of a raw allocation call though. So we call that here. We could just refactor this a little to return the pointer and pass in the size. And then make this a public function, exposed out the header to allow us to request an allocation in the memory map. I think I'm going to do that. It's probably easier. What shall I call it though? Map and map alloc. Find space in the first memory map we can find and allocate room from it. Returns so this is adjusting the Lamini entry. Turn the void pointer and then in memh we'll just drop that guy in here. Do I want to align up to a page size? I probably do. So let's just grab breaks that variable so I know where the refactoring is going to land. Going to align up the length to the page size, and then we're going to use that guy Get rid of you. So look through the memory map, find the first usable block. If it is big enough for our new size, whoops, we've got a spot, let's point here, entry map. Don't need to I think that'll be fine. So that's all pointer arithmetic because it's a void p data. Puts it in the higher half set, uses the base, does a mem set for the size. And then we're going to adjust the page. Change the values in the minor map as this part of the memory is now permanently allocated to our kernel. Yep, all good. And now let's do so that adjusts the max pages available. So this has got to come after the init. See what we've broken. Unused parameter. So create entry map, right? Strange. So this is going to be let me just grab entry underscore map, and it's this guy. It's the size. So the size is going to be this guy. So size of page entries times by number of the pages in the map, rounded up to the page size. That should be it, I think. Let me just get rid of the SLOB source, because that's going to stop the compile. Don't need logs or object. Just need to kill this code here. Can I kill it from there? Nope. And we'll build. Oh, whoops. Would help if we returned that, and then if we can't find it, it's a bit of a panic. That should never happen though. Do I need... I should be fine. So let's just make sure we're not broken anything. Page fault. We broke stuff. I think I know what the problem is though. Wait, why is that? Is this visible from this location? Just try to compile if it is. What don't you like? So it dies in locating space for bitmap? let's just debug what this is doing. Length was is. Just want to make sure I've not screwed up that memory map entry, and I also want to make sure that this address, let's do %x on this guy, just to make sure that location looks good. It should be in the higher half. Locating space for bitmap, create page bitmap. Why would that die? That code has not changed. That's not doing anything crazy either. So what have I broken here? I'm just going to grab this function and save it. And I'm just going to restore what we had. Okay, and then if I take this guy and just put it back here. So this was this size. Try that. Oh, I realize what's happened. It's actually finished. It is dying inside the mem.alloc. So if I just print here, That's good. I'm probably doing something dumb in the code. Yeah, we're inside alloc. So it's something silly in here. Let's just have a check. So we're aligning the length up. Debug that value. Let's make this a little bigger. Map length. Okay, that does not look correct at all. What am I screwing up here? Let's just create that as a uint 64 for now. And then on the include, no, actually, I'm going to keep that as size T. What am I doing? It's just making sure that we're not screwing this up here. All right. Let's debug that incoming length. All right, that looks a bit crazy. So it's probably real though. So it's the size of the page entry in bytes times by the number of pages in map. Let's just print that off. Want to make sure that's still initialized at that point. Five two four 019. I'm thinking about not bothering setting up the bitmap. Yeah, I've got a few things now that I need to kind of get my ducks in order. We've got the PMN, which initializes a bitmap, does page alloc free. We've got this memmap alloc, which is just going to be a Lamine page entry alloc. And then we're going to do SLOB init, which is our SLOB allocator. So we don't really need this guy once we have this working. So did our log actually get an allocation, or did it page fault before the allocation? Yeah, so we're not even getting down to the allocation, actually. What about the size of this guy? That might not be initialized at this point, maybe. I doubt it though. Yeah, 40 entries. Okay, that's good. I'm happy with these two. Grabs the entry, usable. Make sure we get here. Found a page twice. Oh, because the first one wasn't big enough. Right. Which is true, because I think the first page in the list of pages is like 4 or 9 bytes for some reason. Tiny page. All right, so let's see if this location is kind of valid. It might be the mem set. Oh, it's the mem set, dudes. Why? That's why I'd like breaking the variables that I'm using when I'm refactoring and copying. But that'll be the problem. I'm so confident that was the problem that this is just going to work. Watch. There we go. All right, we're back. It was that one silly typo. So now that we have this guy, which acts on the Lamine bootloader, I don't really need to initialize the bitmap. So later on, I'm going to unplug the bitmap initialization code once the SLOB allocator is in. But the fact that that's now up and running, I think we're kind of home free now. I've got that exported, haven't I? I have. Yeah, that's kind of a really handy function to have. That should have been like the very first one I created when I am setting up my PMM a long time ago, but I couldn't understand things as well as I did then, or as well as I do now. All right, so we can move on to the SLOB, but one little thing I want to tidy up. It's in the initialize. Okay, look. Let's get rid of that here. Leave myself a bit of a note there. Alright, I can plug this guy back in now. And why do you not like me? Unused parameters, all good. Let's just void that off for now. And then as well, void that off for while we're debbing. Reaches the end of a non-void function. Unknown types, SLOB entry. I have to do it this way. Okay, so num entries we've now got determined. So now what we can rely on is this mem map. I need to improve that comment on that function. Rounding that up to the nearest page size will just make things easier on ourselves in the future. Okay, so let's just create our initial entry. So we're going to set this guy to SLOB entry pointer, and we're going to create size of entry times line of entries. So that should just do a print on this, make sure we've got a good location for it. Lob in it though doesn't get called, I guess. We can hard plug it in for now. Let's do it after the mem in it. Where are you? Implicit function declaration. Excuse me. Okay. Let's just run that, see if we get that location debug line. It's going to fire off too much logging though. That's fine, we'll check the log file. Oop. So should come after all these memory regions. So head location, there we go. So we're in the higher half. And then that's our located SLOB entry map. And that's what we want. So that's now sitting in RAM, nice and cozy. And then what we'll do is walk the list again. Hold on, let me think. Yeah, this is fine. Initialize the entries. So entry index. Key head points at the initial so we can take this directly from the entry, I believe that's in bytes. And then what we're going to struggle with here is the next is the address of where the head entry index +1 we're gonna leave it null though. Yeah, it only points to its next neighbor when it has one, basically. Just to be quite explicit here. The end entry has no next. Let's debug log the setup of the entry. So we're going to say setup entry size. We'll dump the add entry index length. And we'll dump the next pointer. think that'll do it. Let's give it a go. I just saw that get spammed in the log. So SLOB entries, here we go. Size, 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 so that's all in bytes, and we're not incrementing the entry index on the loop. So that's our first problem. All right, there we go. You can see that next pointer now incrementing at the size of the actual struct. We've got some nice big chunky SLOB entries in there. So that all checks out, and that last entry should not have a next, and that's why I thought I was going to be off by one. What we should get is the last entry has a nil. There we go. So it's got a size, but it hasn't got a next because it's the end of the list. That's what I was looking to see. Now, that is fine. So, allocate enough room for all the initial SLOB entries. And then we initialize the entry. So now we've got a bunch of SLOB entries ready for Alex. So, let's document this. Initializes the initial SLOB entries according to available areas of RAM in the Lamine memory map. And that is what we're doing. I'm just, let's see. Love this song. Poor YouTube. All right. So the initialization, job done. Now let's do the initial allocation logic. So starting at the head of the map, we're going to find a free blob. So let's do start at the head, and that advances to the next node in the list. Now, if the node that we're on is less than or equal to the size that we've requested, now, yeah, we're not doing page stuff here yet. That's going to be version 2. So this is just going to be any number of bytes that you want to allocate will respect. It could be as little as 1 byte if you wanted to. Okay, it's playing this in my head now. Right, so step 1, once we've found a location. So we've found a chunk, an entry in the SLOB map. Found an entry that can fit our request. Let's split the node. Now, this is interesting, because when we split the nodes, we're actually do we split them? Okay, so what do I mean by split the node here? So we're going to resize this node up away from its base, and we're going to reserve actually, you know what? I did kind of want that to be packed. Oop. Because what we need to do is get a total length that we're going to allocate, which is going to be the size of the SLOB entry plus the size that we've requested. And we're going to move oh, that's silly of me. We're not storing where the base of the chunk is living. No problem, we're going to fix that right now. So entry base uint64. We're going to set that in the initialization. So going to grab that from the Lamini map. Hey G, how you doing, dude? Do I have the Twitch chat open on my Oh, there we go. There we go. I've just put the chat on the stream, so it appears on the VOD. You just got in? Nice. How's your Monday going? Gone? We're finally getting round to doing the SLOB allocator. So we've just finished the initialization, and now we're going to do the malloc. Move the base of the entry up by our new allocation size. So base is going to get pushed up by the total size after we've squeezed in our new header. Today was busy. Yeah, I had a super busy day too for a Monday. Well, my schedule at work is locked up for a few weeks. Like, there's no free time. There's always like a big to-do list that I come into every day, as I'm doing Google Cloud training interweaved between my daily tasks. Okay, so I'm just kind of emulating this in my head now. So we're pushing the base of the chunk up away from its current location because we're allocating that space. And we're doing it by the size of the header that we're going to slot into memory. So I kind of need to be a bit cheeky here. Let's make a pointer to the header. So this is going to be pass this to a pointer, and we're going to start with the base, and we're going to push this up into the higher half to get physical memory access. And then this header is going to have its current base set to the existing entry's base, but its size is going to be our new total size. So let's just comment this. Set up the new chunk that's split from the existing chunk that we've found. Oops, set up the new chunk. It's now split from the existing chunk. Okay. So we're setting up the header. So we're at the same base that we found. We're claiming that base. We're setting our length to the new allocation size that we now have, which if we say that the size coming in was a 1 byte request, then our total size is going to be 5, which is rightly so. And then we shift the base of the existing node up, but we also need to decrease its length by our new total size. And now we kind of need to get a memory location after the header. So we're going to take the base call this Alec, I think. So this is at our existing header of the base. And we're going to add onto this size of SLOB entry. So that gives us a location just after the header, and then we're fine to return that allocation. Let's just make notes in the free. So to do, read the header from the pointer. So this is interesting. I can kind of see clearly now how the next part's going to go. So I wonder what happens when you've actually depleted an entry. I guess the size check will always fail and then cause it to skip to the next entry. Yeah. So that's fine. So is this, we can test it though. Yeah, we'll have to draw out some debugging lines for this. Do the edge case testing. Oh, moving as in, have you moved house or moved jobs? I'm due to move myself in a few weeks' time. Oh, you bought a new location for your business. I see, I see. Oh, that sounds fun, dude. Do you have like a lot of decorating to do or renovations to the new place or? Oh, I hope the music isn't too loud, by the way. Let me know if it's a problem. Cool. All right, let's do some code docking. Let's be a good OS dev for the community and let them know what this stuff is doing. Allocates a new SLOB entry, and the first available SLOB entry we can find that fits our new allocation size. Did we set the next of the header? No, we didn't. We should do that. So because we allocate left, our next is always the guy that we're splitting from. Yes, it is. Okay. All right. And then, hold on, so am I doing this correct? Set the base. And we're forwarding by the header. Oops, I'm not going into the higher half, so we should do that. Which makes me realize, actually, huh. Yeah, no, that's fine. It's fine. Kinda having to visualize this in my head. What I should do is draw this out after I've created it. Because this is kind of like, it's going to be the first semi-serious allocator that we can use in the kernel. And then I can upgrade this much later down the line. I think that's it. Allocate some new SLOB between the first row, so I do defined. That fits our new allocation size. We split the found entry and insert our new entry at the start of it. Okay, so our free is going to be interesting because this is where I kind of want to bend the rules a bit and I want to merge sibling nodes. But I don't have to. I can merge. It might be that I just need to merge to the right. Oh, I've got to be careful here. So, just thinking like if you're in multiple allocations and you've only got next pointers, so these two, okay, so this is going to have 10 to 20, and now this is 20 to 100. So this is what happens after a couple of allocations into the entry. You're going to get SLOB 0, which is like your big chunk that you begin with. And SLOB 1 gets created at the beginning, 0 to 10. And then we've resized SLOB 0 to 10 to 100. So the base is pushed out to that location. And then you come in with another allocation, and it's found SLOB 0 to be of the required size. So because that base has been adjusted, it grabs another 10 bytes and then pushes SLOB 0 out to 2100. Now both of these are going to say that their next pointers are SLOB 0. Does it matter though? It does matter. It really does matter. If you free up SLOB 1, so in memory it's going to look like this: SLOB 1, and then you're going to have SLOB 2, and then you're going to have SLOB 0, which got resized and pushed up. If you free SLOB 1 by itself, you can't adjust SLOB 0. You're going to create an empty space in RAM at that location. And this is kind of where you're creating new entries in the SLOB metadata away from what it was initially designed for. Let's push this on a little bit and just do SLOB 3, and then I'm going to mimic freeing SLOB 2. So if SLOB 2 gets freed, let's just say this is 4 bytes, that's 4 bytes, this is 4 bytes, and that's 100 bytes. So SLOB 2 becomes free. Does it matter that I can just grab a piece of memory for that new SLOB entry? So like it can just call, does it need to be malloced though? So when you free, you need to allocate space. Or do you? Shall I just make this simple and make them all in the same list? Just making a note for myself here that the head of the list that we store globally here, which I don't think we're setting, are we? Oh, we do. So that's gonna be SLOB 0, and it's always SLOB 0. Should it be SLOB 0 though? Should the head be moved? No, it can't be moved. It needs to be it needs to be the beginning of the list. Which poses a problem when we come to free the elements. Okay, we can solve this. We can solve this. So, to use this information that we have here, so p head is always here, SLOB 0. Call it p head. I don't feel that's correct, saying that the next is SLOB 0 and SLOB 2. So when you create SLOB 1, your next is SLOB 0. But when you create SLOB 2, your next is SLOB 0, but P1's or SLOB 1 entry is now SLOB 2. But how are you going to know to adjust SLOB 1? I'm thinking to just having a master list of SLOB entries that are kind of all auto-wired up to themselves in order. Some are allocated, some are available. Let's do 20 to 30. I'm just trying to envision this with the 3 entries on. Whoops. So ideally, to walk this list correctly, I don't want to see these SLOB 1 and 2s wired up to SLOB 0. Because the way they live in RAM is 1 points to 2, 2 points to 3, 3 points to 0. I'm kind of making a good assumption too that when I'm walking the list of entries, it's in linear order. So, you know, the first entries are the earlier parts of memory and the later entries are in the later parts of RAM. So it's kind of like in an ordered fashion, which helps. All right, how do we do this? Let's draw out each allocation. Okay, so SLOB 1, you got allocated next door to SLOB 0. SLOB 0 is currently the head, and your next is SLOB 0, and SLOB 0's next is whatever's later on in RAM, which is fine. To the right of memory. This SLOB got implemented to the left of memory, so it's fine to just point this new thing at SLOB 0, and SLOB 0's next does not change, because we've not modified the right side of SLOB 0. So the problem occurs when SLOB 2 comes in, and we've got some miswired things. So ideally, SLOB 2 should point at SLOB 1. But how would we have got there? Because we're unaware. The list that we're checking is here. Oh, I think I've just solved it. The head changes to SLOB 1. And if the head changes to SLOB 1, oh, we do need to mark it as allocated though. Which we can set it to 8 bits for now. So what we can do is point the head at the new allocated SLOB entry 1. Let me just run through this in my mind. So SLOB 2, SLOB 1 got created. The head is still at P0 here, but if I put the head at SLOB 1, then the iteration begins at SLOB 1, but we want to skip that SLOB because it's allocated. So we can just check that. If it's allocated, go next, right? And then you land back on SLOB 0, and you're now allocating on SLOB 0. And when you push left, oh, your SLOB 2 is actually, it's like this. Because it squeezes in on the left of SLOB 0. So SLOB 2's now correctly placed left of SLOB 0 with the P next pointed at SLOB 0. That is correct. But we have modified the previous SLOB. That guy should point at this guy, which we can do because we can save the previous pointer to the entries. Will that work? So P head, let's just write down here what we're changing the head to. So SLOB 1 is now the head. And then when 2 gets introduced, the head is still 1 here. But why is it still SLOB 1? I mean, it's correct. Do I want to say that the head, which is SLOB 1, equals SLOB 2? And then if I add SLOB 3, which again goes to the left of SLOB 0, so the head SLOB 1, well, what we want to change here is SLOB 2's next, which is going to be pointing to SLOB 3. So the head doesn't change. We can simply say there that when you're allocating and your SLOB entries are less than doesn't help that the SLOB entries that we create are positioned in memory at an arbitrary location, because I could have done some testing on the memory addresses just to see where they are linearly in memory. I just realized that this text will be quite crap on the stream, sorry. Yeah, this strategy isn't really lending itself to be, it doesn't fit. There's actually 2 actions we want to set here. No, it's actually, no. Why am I choosing to adjust the head and set it to SLOB 1 here? Why? But I wouldn't here. Like, why am I thinking about it in linear terms? I think that's what's confusing the matter here. What I could do is that whenever I create a new SLOB entry. I can just set it next to the head and set the head to the new SLOB. Would that work? So it would work in this instance. Okay, we created SLOB 1, so we push the head down, and SLOB 1's next points to SLOB 0. So the walking in the next iteration will be fine. The head begins at SLOB 1. We can check if it's allocated. Yes, it is. We move on to SLOB 0. Okay, now we've found an allocation chunk. And then what happens is that gets pushed to the left of that chunk, and this is where it's going to change a little. So I could say, okay, SLOB 2 get created, and P head now becomes SLOB 2, which is going to point its next. Where's its next going to point to? Should it be SLOB 0? It can't. To maintain the list, it needs to point at SLOB 1. So the way it's kind of set up in memory is just, it's an inverse of how I'm joining the list together. Right? So SLOB 2 physically in RAM is to the left of SLOB 0's chunk, and it's also to the right of SLOB 1. But I can point the head at this new chunk entry and tell it that its next is the existing head, which is SLOB 1. So when new SLOB entries come into the system, I'm prepending them to the list. And then it would maintain that the walking of the list is the integrity of the list is intact. So the iteration of the list will become start at SLOB 2, and then we iterate over to SLOB 1, and then we iterate over to SLOB 0. And then in this instance, when you get SLOB 3, okay, the head is now at SLOB 3. So the head, SLOB 3, over to SLOB 2, over to SLOB 1, then over to SLOB 0. It's just going to make for a shitty allocation routine because you're going to be walking through all of the allocation blocks, which is kind of lame. You don't really want to do that because you know at that point that it's not free memory. Like, why are you walking that list? Okay, so that's not going to scale. 1,000 allocations is a horrible for loop over 1,000 indexes with 1,000 ifs before you even get to the block that you want. When ideally you just want to go, what is the first free chunk? Found it. Do you have room for me? Yes, I do. Allocate, return. It's just a manipulation of these SLOB entries. So let's keep the SLOB head at SLOB 0, which is always a free space. And let's disconnect the thinking away from these new SLOB entries being pointers to the chunk around them. So let's just pretend each SLOB header is just my base and my length. And I am going to point to... Should I point to where I came from? Like, should slob 3 down here, tucked away, point to, or should I say slob 2, sorry. So should this guy be pointing to that, hey, my parent slob is slob 0. So let me simulate that then. So when we come to free slob 2, knowing that my parent was slob 0, I can't resize slob 0. But what I can do is I can define this area of memory as a new isolated chunk of memory. So this is where I could say, okay, we've got a new free available chunk. So what I'll do is adjust the head to point to this location, point to slob 0 as the next, which is the free space. And this slob here is also free space. So when we go to walk the list, we're actually starting at slob 2, which is now available. And hey, we might fit. That works. Now, what's horrible about this is that when you're freeing multiple locations, you're constantly creating slob entries the size of those blocks. So eventually you're going to end up with this really fragmented list, really. Your slob list is going to be blocks of like 10 bytes free, 20 bytes free, 4 bytes free, 5 bytes free, depending on how your allocations happened. Now, when that happens, it would be quite easily to defrag the slob entries. Because when you test for where the base of those entries are, the length of them, you know that if the length of your base marries up with the base of your next slob entry, that defragging is going to be horrible because the list is out of order. It really depends on the order of allocations and frees. You know what? I might make it a tomorrow problem and just get the initial reallocation logic in place. So what I like about it is that when you free an area of memory, we just create that as a new slob entry. And prepend it to the list. Which means we don't need... We can kind of have a different struct. I kind of thought we were going to do this as well. Do I need base, or do I just need length? I just need length, because base is kind of inferred. Like, I know where the base is, because it's wherever the slob header is allocated, minus the slob header size, and that's my base. So I don't need to store base in the header. So, slob header It makes the metadata smaller here. So like here, found an entry that can fit requests that split the node. Total size is the size of a header plus the size, and then allocate, get a pointer to the header. Don't need to set the base length, total size, that's fine. Don't need a next pointer. Get the user's memory location after the slob header. We'll do this here, because then we'll reuse the base location here from pnext, because we haven't adjusted it at this point. So we're skipping over the slob header. Whoops, gotta be careful there. And that gets the actual address, and then we're adjusting the base and the length of the actual slob entry. So that works. So the act of freeing. So this slob entry becomes a new free part of RAM. So prepend this to our slob entry list. It's kind of crude. It kind of works. It's just, it's so nasty in fragmentation that when you start ferociously allocating and deallocating over time, you're going to get a really finely grained, massive list of tiny little memory locations that are now available. And that can be solved in two ways. I can defrag every time I go to free memory. I can look at defragging the entries at that point and merging them. Or I could wait to a certain point in time when there's a certain weight, like when there's more than 100 entries in the tree, balance it by merging them, you know, and then running. It's kind of like a metadata garbage collection. Would kind of work. I think what I'm going to do is just implement this crappy way to begin with, get to a point in the OS where I can render graphically this list of things or this map structure, and then when I can visually see what's happening to the RAM structure, I can start chewing on that visualization and thinking about how I'm going to merge yeah, because this is getting out of hand pretty quickly. Free simply takes, I don't use the word simply, that's just silly. Allocated entry and makes it available by creating a new slob entry and prepending it to the list of free entries. Yeah, what I've found and what from the discussions they have on the OS Dev community channel is that there is a base algorithm that people start with, like I'm starting with now, like this slob idea, but it's bent ever so slightly to how you have your current memory set up. For example, this allocator does not lend itself to page sizes. And the reason I've left it out from allocating pages is because it drastically complicates my thinking at this point. So I'm going to add that in after. MMU style page allocations and allocating from a list of pages before just grabbing a massive chunk of RAM, you know. It's so easy in my brain to just keep thinking, oh, it's just this, you know, it's just that, but it's a lot of intertwined concepts, like the MMU 4K page size, virtual memory maps, the physical memory manager, and then whatever algorithm that you want to plop in the middle of all of that stuff, right? And it's a lot of stuff, a lot of logic intertwined. And that's where it gets complicated quickly in my brain because I'm not too experienced in all of those areas to know exactly what I'm dealing with. So I'll do it this way at the moment, which does free me into getting on with the OS. Like I can live doing a malloc and a free, no problem, knowing that my RAM is getting fragmented to shit later on. But I can do that refactoring later. You know, I can upgrade the way malloc and free are working. So, yeah. Grab the header from the previous bytes of this memory location. So we've got to remember we're in the higher half location here. Just checking that I've got my higher half offsets in the right places there, and I definitely have. All right, so let's grab it. So this header is going to be at the pointer address minus the size of SLOB header. Again, it's still in the higher half, so now we've got access to the length, and we're actually at the new base. So that header is in fact the base address of the new chunk. So this is interesting actually. When I create I'm actually going to malloc myself here some memory. Like I need a new SLOB entry, right? And here I can say the base is the header. Yeah, that'll work. That's the beginning of the header. But that's, I've got to take off the offset now, because that offset does not, it shouldn't use the offset until you start using it. Yeah, so we're taking it out of the VMM higher half there to grab the base. And then so the length here, did we set the length to the total size? We did, so we can just grab that from the header that we just extracted. And I think that's it, right? Base and length. Oh, and the next, so prepending, so next is going to be the current head. And we're going to shift the head. New entry. We kind of need some spin locks here, by the way. So eventually when we multi-core this, we'll have to come in and just put a spin lock around this structure modification here. Again, that's a tomorrow problem. We can develop it for those needs as we come across them. Again, I can't, even though these, I know that these are going to be tomorrow problems, there's too many to think about. So we'll get the XP first, and then we'll adjust as we circle back. Let's put a to-do here though, let's not forget. I need a spin lock to protect the structure change for multi-core. All right, I think so. That's grabbing that out. That's in the higher half. Yeah, that head. I think that's all good. Damn, I think we did it. Our initial implementation. Let's just put over time. There's going to be a lot of small variable entries as memory is freed until we implement merging, defragging stuff. Okay, kind of happy with this. So in the alloc code, so we'll turn off so use SLOB. This is so that I can switch between different memory algorithms, by the way. So I'm using these toggle flags to just say compiled using bump allocator, compiled using SLOB allocator, and the alloc will wire up malloc and free to the right allocators. Do I even need that else block? I don't. All right, let's grab SLOB each. We'll do SLOB, alloc. The initialization, how are we going to do this? I guess we can lazy in it. That wouldn't be a problem. Easy peasy. Saves me wiring up standard initialize functions in the interface of the memory managers. So we might want to do that later on, but not for now. This is fine. It'll work. Okay, so let's see if that just clicks in then. So if we just change this to use SLOB, alloc should compile. So that's malloc, SLOB free, all good. Now, are we feeling brave enough to do this? So we have a bunch of kalloc calls in the kernel. And ideally, we just want to change these to malloc. Let's see if we're compiling first. Have we forgot to return something? Integer from pointer without a cast. Really? You can't infer that? Wait, we didn't... We didn't return 0? Redefinition. Where am I redefining things? Did I break the flags? Use bump is 0, use SLOB is 1. Malloc free. Why is that showing as compilable code? Hello? I change that to if not defined. Oh, of course, silly me. Gosh. Get rid of that def. Okay. Did we break anything? Yeah, we did. Is it because I've got some test code in the kernel C still? Let's go have a look. I do. So I didn't want to do this right now, but probably it's a good first start, isn't it, on testing if you've broken your memory allocator. Let's make sure that that's what was breaking. Yeah. So, hello, world. CLS. Hello. Nice. Unknown command. We still need to do the cursor on that console too. That would be nice. All right, so let's just try a malloc 1 and let's just see why it's crying. So let's do void pdata from malloc. Let's do a kprint f on that memory address. Whoops. And let's just see if we're getting death in the malloc. All right, so where are we dying? It's probably a cast or something we're doing wrong somewhere. SLOB malloc, here we go. Let's just dump in here. Make sure the init is being hit, and then we'll do some basic logging for now. Try and zone in on where we're dying. Yeah, finding entry. Wait, it didn't hit this. Did we see initializing SLOB, or am I seeing things? No. Wait, why is that failing? Or is it not making it to the console? It's saying it's already a init. So why can't I test that pointer for 0? Is null? that kind of the problem? Okay. I'm going crazy here. It's already a knit. How? Because the variable has a memory location. Why is it set though? What am I missing here? Um, I should really do that on that header. Oh, I might get some typecasting problems there. Do the no check macro. Why does that have a value? This is wild. Like if I do this, what does that mean? Yeah. Initializing SLOB. So why, when I set it here, but not on program start? Ugh. I'm kind of over that problem. All right, so we're getting the initialize run now. We've got the finding entry, and it's returning p data as 0, which is not fun. We're failing at the first hurdle. Okay, print f here. Kind of a scary situation to be in. I don't expect to see that for a long time. I wonder if we copied the size over when we were passing the memory map. No memory available. Nice. Okay. So we failed. We failed! Return if length of the memory is less than the size that you've asked for. All right, there's got to be something wrong up here then. So when we're creating the map, entry length base. Let's just dump the size that we're actually looking for here, because we got some like memory corruption happening. Could have. Let's make no assumptions. Finding entry for size 1. Okay, that should absolutely should be working. Yeah, that should be hitting the first page it finds. So let's debug these. So length. Can be very surprised if that length isn't initialized. Oh, I must be tired. I'm starting to like fail at some really basic stuff here. So if the size that you've requested is less than or equal to the length of the page, then you can allocate. Okay, there we go. That all checks out perfectly. Initializing SLOB, finding entry for size 1, p data that we got back from malloc is in the higher half at 13008. Wonderful. Let's do that repeatedly, and then we'll flex to free. And that's where things are going to be very interesting with the whole fragmentation thing. So do this in the kernel. Let's do 10 byte allocations, and then I'll do bigger ones. Okay, so I just want to kind of see the memory addresses going up there. So 08, 1A, 2C, 3, 50, 62. Pretty nice. What about 1,000 bytes? It shouldn't really matter. Let's do 10,000 bytes. Like, that has got a lot of room to play with. It's got the whole of RAM. Yeah, and we can see the sizes there now going up aggressively for that 10,000 bytes per allocation. Cool. So how about constantly allocating a 10K block, freeing that allocation, and then the next time we come around, we should be picking up that same entry address. It should be instantly reused, right? Because at that point, when I free, I'm saying, okay, let's free up 10K. And then the next 10K allocation that comes in should go, oh, I've got a nice 10K block to use. So we should at least see the same memory locations for this run. Finding entry for size 24. Where's that come from? Oh, because of the free. Oh, let's just take that logging out because it's getting a bit too noisy. Actually, no, it's fine. I mean, we can see actually what we're looking for. So the reason you're seeing finding entry for size 24, because we're invoking the allocation for the new SLOB node, right? So down here, we're doing SLOB malloc. But it's perfect. Finding entry for a size 10K, and that P data look is constantly reused. So it's being malloc freed, malloc freed, malloc freed. And it's beautiful. Like it's working perfectly. Now, if I, what I want to do is at the end of that run, so next test will be, God, there's so many like edge case unit tests that you can do on this logic. I probably need to think about that. Just setting up a bunch of unit tests around it all as a closed unit, a closed system. So at the end of that for loop, it frees that last node. And then what I'll do is I'll free, or I'll malloc 1001 bytes. And what that will do is it will cause the next allocation to not fit the 10K block that is available to it, and the last allocation should be further on in memory. So we'll have a look. And it's actually allocated at the same location. That's bad. That is bad. Because if I ask for 20K, well, let's just bump this up. It might be enough by one error. If I do 1,000 and 10,002. No, it's got the same location. Okay, that is a bug. That's 100% a bug. And let's go debug Y. So, let me just look at here. I'm setting the head to this new entry, which has a length of the header. Oh. No, that's fine. The p header's length. That's the length of the total struct. The base. Let's just kprint here and say created new entry at size, and then we'll do whatever's in the header. Tally that up. It should. $1008. Finding entry for size 10,002. Oh, because I need to kind of prepend these logs a little. Let's just get a bit of this action going, where the logs look a bit more digestible. I probably don't need to do that many either. I can turn that down now. Creating new memory at size 10,008. Okay, that's wrong. But it's right though, because you... Wait, so was my test just invalid? If I do 10,100 on the last one, I see now that it's 1,000 what you asked for plus the header, which is 8 bytes. So it is using the same slot up to 1008. I'm kind of like getting caught out by my own logic here. Now it's working. Finding an entry for size 10,100 and you get pushed way further up in RAM now at 159A0. Now if I ask for, just to confirm this, 10,008, which is the size of the available block plus the header size, you should get the same location. And at 10,009, you should get bumped up. So there's same location, 13,008, and then 1 byte outside of that chunk, you're going up in RAM. There we go. We got pushed up to 159A0 there. So that's perfect. I kind of wasn't thinking about the logic of what's being freed, it's interesting. We truly allocate what you asked for plus a header, and when you get freed, it is that header plus what you asked for. That is now a free chunk. Perfect. Yeah, that's it. So it's working. It's working perfectly. I think what I'll do is I'll find those places in the kernel that are using kalloc and just migrate them off into the new memory call and see if the kernel is happy booting. So kalloc, what are you doing? Spin locking. So that's all the PMM's stuff. So we shouldn't be using this. So I'm going to replace these with mallocs. And I'm going to get rid of these calls here. I don't even think we have key3. No. Void kp alloc. Bump C. Oh, I was using that. All right, let's just leave them in for now then, but only allow a little weird that I cast that to a char, but whatever. Can I cast a pointer from integer of different size? Excuse me? Wait, why is that int? Oh, is it picking that up from somewhere standard? PCI, yeah, okay, phew. Let's cast that to pointer, and let's bring in alloc. I kind of need to clean up those headers as well. So there we go, we've got a compile. So we should, so that's the keyboard driver and the PCI scanning that's been affected. And it's fine. Hooray! We're on our new memory manager. Let's go. Sweet. We've got a malloc and free powered kernel now, and it's using SLOB. What a win. Dude, I'm so happy we got to this point because I now have a platform to use malloc and free throughout the kernel, and they're perfectly going to work exactly how they say on the tin. Just not very optimally, but we can optimize that later. Beautiful. Right, let's just check that in because that is a great piece of work tonight. That is from a lot of thinking during the week in my downtime at work. And finally getting the time to just put that code in. My branch is behind. Scary. That's weird. It did say it pushed. Why did it say push failed? Let me go check. GitHub. Commits. Oh, because I updated the README online last week. That was it. I got a bit scared then. Okay, wonderful. Wonderful. I love this. So the only thing now I need to do some cleanup of is unpicking the bitmap initializer. So I don't need that now. So we've kind of like upgraded the way we're managing memory by a large stride now. Yeah, and I don't need this bitmap stuff. So this is all like gone away. Nice. Oh, let's get rid of all these kprintfs in the actual code. That is not good. That one's fine. Okay, cool. I think that's a good place for the night to stop, actually. Just one last run. Nice. We are back in business. Cool. All right, well, thanks for showing up, G. That was a really good, productive stream today. Can't promise when I'll next stream because it depends on how stressful work is and what time I have. But yeah, I'm going to push this up to YouTube for my YouTube viewers and then try and schedule in another one before the weekend, maybe. But yeah, thanks for turning up, buddy, and I will see you in the next one. Take it easy.